All right, so here's our next example of integration by substitution with our little introduction discussion. As always, integrals don't play well with radicals. So the first thing I'm going to do is rewrite. It has nothing to do with the calculus. We're just going to rewrite this without the square root. I'm going to write this as 20x to the third, and then write this as x to the fourth plus 5 raised to the 1/2 power. Integrals don't play well with radicals, and so I'm going to rewrite that with exponential form. All right, so we have what looks like sort of the product rule, but there is no product rule for integrals. Use substitution. This is not a basic form. For this semester, this is really easy for you guys. Eventually in Calc 2, you have all these different techniques, and so you need to know what kind of problem requires what technique. For here, it's either a basic form or it's a use substitution. Those are the only two games in town. This is not a basic form, so this is a use substitution. If it's a use substitution, then the first thing you write is let u equal. At least you get credit for having done let u equals. Now, the rule is, what do you let u equal? If I have a quantity in parenthesis being raised to a power, let u equal that quantity. Notice also, let u equal, which is it? Remember? Let u equal the larger degree. See, what's going to happen, we know what's going to happen. You're going to find the derivative. When you do the derivative, you lose a degree, which is what we want to have happen anyway. So we're aligning this to force it to do what we want it to do. So we've let u equal the quantity in parenthesis, the quantity that's being raised to a power, the quantity that's being acted upon by this other function. This quantity, x squared plus 5, is being acted upon by the radical function, the square root function. This is being acted upon by this 1/2 power function. The technical word is this is the argument of this other function. So let u equal the inner argument. Now we need to find the derivative of u is equal to be something times derivative of x. But what is the derivative over here? Well, the derivative here is 4x to the third. So the derivative with respect to u is 4x to the third, which is the derivative with respect to x. So what have we translated so far? So far, we have this. This we know how to translate. That is the u. What is now left unaccounted for? We don't yet have 20x to the third, and we don't yet have dx. We're close. We almost have that. See, we have 4x to the third dx, but we want it to be 20x to the third dx. This is what you are allowed to do, and only this. You are allowed, once you form this differential line, once you form the differential for this differential line, you are allowed to multiply both sides of this differential line by any constant except 0. You can multiply both sides of this line, both sides of this expression, by 105 if you want to. You can multiply both sides by -8 if you want to. You can multiply both sides by 15 if you want to. You can multiply both sides by 1/4 if you want to. You can multiply both sides of this by any constant, not 0. You may not multiply both sides by x. Students try it, it's never correct. You may not multiply both sides of this by u. You may not multiply both sides of this by t. You may not multiply both sides by any variable. You may multiply both sides by any constant. And so the question is this. We have 4x to the third. We want 20x to the third. What multiplier do you need? Duh, the multiplier is 5. So let u equal x squared plus 5. That implies that du is equal to this expression, but we don't want that expression. We want to multiply both sides by 5. So this implies that 5 du is equal to 20 x to the third dx. And now what we have here is precisely the leftover bits. As soon as you form this differential line, you have one goal. As soon as you form this differential line, du equals 4x to the third dx, as soon as you form that differential line, you have one goal. Your goal is to, on the lower right, create whatever is left over. Sometimes you can do that with one step. Sometimes it takes 2 steps. I'll show you how that works. But you need to create whatever you have left. In this case, the way you create that is you multiply both sides of the equation by 5. And I will say this every time. I will say it every time, every time, every time. As soon as you have this recreated, the substitution is exact. I'll say that every time. The substitution is exact. As soon as you create what's left over here, the substitution is exact. Because now you can substitute. You can change into the U language. How do you say garbage to the 1/2? That's U to the 1/2. How do you say 20x to the third dx? How do you say 20x to the third dx? That's 5 du. And because constant multipliers multiply along, I usually just throw the constant multiplier out front. You may, if you wish, put it inside. I like to just go ahead and throw it out front. Constant multiplier is just going to multiply along. So 5 du, right? 5 du. And now, constant multiplier multiplies along. This is straightforward. This is easy. This is the power rule. The power rule says you add 1, divide by the coefficient you just created. Now, the only simplifying I'm going to allow you to do is with these coefficients. If you just want to leave it like this, so much the better. If you want to leave it like that, that's fine. If you want to leave this as 5 times, what was u? You do need to go back to the original language. U, go back to the let statement, x to the 4th plus 5. If you want to simplify the divide by 3/2 means multiply by 2/3, that's fine. But I'm telling you, if you try to simplify this, you are not getting full credit out of me. If you try to simplify this, you're not getting credit out of me. There are reasons I'm doing that, and there it is. So don't simplify this piece. If you want to simplify the coefficients, I don't care about that. So there's our solution. The rule is let u equal the quantity being raised to a power, the quantity in parenthesis, the larger exponent, and then create the leftover pieces. And when you do, the substitution is exact. Substitute, antiderivative, go back to the original language, and you're finished. All right? So the only thing left to do now is rummage through a few examples of this. And I'll click through a couple of them here, and then we have several videos with several examples of different varieties. So let's go ahead and do a couple more here. Remember how I said sometimes it's a 1-step, sometimes it's 2 steps? Here's a 2-step job. Suppose we have the antiderivative of 7. Let's go 7x. Cosine of x squared. This is not a basic form because cosine of x squared is certainly not a basic form. There is no product rule for integrals. This is not a basic form. So the only way we have to solve this so far for this semester is to, and for all of this semester, is to substitution. And since this is substitution, we're going to let u equal, and we have a choice. We can use 7x, we can do cosine, we can do all kinds of things. The quantity in parenthesis, x squared, is being acted upon by cosine. If I have cosine of x squared, if I have secant squared of x squared, if I have x squared inside of this trig function, x squared inside this trig function, that's a really good bet. A really good bet is that this is going to be let u equal x to the second. Notice also, This is degree 2. This is degree 1. Let u equal the larger degree. So we've accounted for this piece. How do you say cosine of x squared in the u language? The way you say cosine of x squared is cosine of u. So we've translated that part. But what's left untranslated is 7x dx. That's what we need to create. We need to create 7x dx. Well, first, the derivative. The derivative with respect to u is 2x times the derivative with respect to x. But the problem is we don't want 2. We want 7. Well, you can do this with a single multiplier. You have to choose the fraction. But early on, what I like to do, I like to think of this for students, if you're any confusion at all, I like to think of this as being a two-step job. This is a two-part job. First, get rid of the number you don't want, and then create the number that you do want. Get rid of the number you don't want, create the number you do want. We don't want the 2, so multiply both sides of this equation by 1/2. 1/2 times 2 cancels. Everybody follow that? Multiply by 1/2 to get rid of the 2 you don't want. 1/2 times du is 1/2 times du. 1/2 times 2 cancels. So get rid of the number you don't want, and now create the number that you do want. Multiply both sides by 7. So this is 7/2. You do this often enough, you'll learn how to do this in one step, but that's okay. Just use 2 steps if you need to. But notice, we have now created the leftover pieces. The substitution is exact. As soon as the substitution is exact, you're ready to substitute. How do you say 7x dx? 7x dx, that's 7 over 2, constant multipliers multiply along, du. How do you say cosine of stuff? That's cosine of u. Got kind of crowded there. And that is the problem stated in the u language. This is a basic form with a constant multiplier that multiplies along. What's the antiderivative of cosine? The derivative of sine is cosine, so the antiderivative of cosine is sine. The others are the ones with the negative sign, negatives. Sine derivative is cosine, cosine integral is sine. So the antiderivative of cosine is sine. And then go back to the original language using the let statement. 7/2 sine of x squared plus c, and we're out. So that's the basic notion of integration by substitution. There are variations on that theme, and as you gain more experience and gain more tools, you learn not only how to use the other tools, but you learn how to use substitution in concert with the other tools. As you learn more basic forms, you'll learn how to put the substitution in with those other basic forms. But substitution is a basic, one of the standard techniques of integration, and what we've talked about here is really just sort of the basic notion, when to recognize it, and then how to know what to let u equal. Here's the thing. If you let u equal something and it doesn't work, don't give up. Let u equal something else and work that out. So that's a basic introduction to the integration by substitution. And then what's going to follow are several videos with several examples of various types of substitution that you should be able to become pretty adept at.